As we discussed in the previous video, today we are going to see the theory of linear homogeneous equations. So let's continue with this theorem. Say f1, f2 and so on up to fmb, any solutions of the following linear homogeneous equation. You already know the left hand side of such an equation looks like this and the right hand side is 0. So that's why it is homogeneous, because of this 0 right hand side. If these are all solutions of this equation, then C1 F1 plus C2 F2 and so on plus Cm Fm is also a solution, where these Ci's are constants. That means these are real numbers that do not change with x, where x is the independent variable of these functions, say. And such a combination is called a linear combination of these functions. So that means this theorem is saying that if you have any number of solutions of a linear homogeneous equation, then any linear combination of those solutions is also a solution. For example, if you consider this linear equation second order, which actually we saw many times before, both sin x and cos x are solutions, which you can verify very easily. And that is why by that theorem, C1 sin x plus C2 cos x will also be a solution for any real numbers C1 and C2. In particular, for example, 5 sin x plus 6 cos x is a solution. Or for example, consider this third order linear homogeneous equation. The third derivative minus 2 times the second derivative minus the first derivative plus 2y equal to 0. You can verify that e to the power x, e to the power minus x and e to the power 2x are all solutions. That is why by that theorem, this linear combination, here this one is C2, okay, although it looks like e. This is also a solution for any real numbers C1, C2 and C3. For example, 2 times e to the power x minus 3 times e to the power minus x plus 2 over 3 times e to the power 2x is a solution. To get to the notion of general solutions of linear equations, next we are going to need this definition. Here we have n functions, any functions. They are said to be linearly dependent on a closed interval in the real line if there are that many constants as many functions you have, n constants, not all 0, not all the ci's are 0, such that the linear combination of these functions using these constants is equal to 0 for all x belonging to this interval. That means this linear combination is also a function of x after all, right? Now, no matter what x you choose from this interval, you will continue to get 0. But at the same time, not all the ci's are 0. If they are all 0, obviously this will be 0. But that's not the case. If this happens, then we say that these functions are linearly dependent on this interval. This notion of linear dependence is exactly the same thing that you have in linear algebra. The vector space in which you have this linear dependence has functions as vectors. For example, you can consider these two functions x and 2x. They are linearly dependent on this closed interval 0, 1. That is because 2 times the first function x plus minus 1 times the second function 2x equals 0 for all x in this interval. Here there are two functions, so accordingly we have C1 and C2. C1 is 2 and C2 is minus 1, both of which are non-zero, although we need at least one of them to be non-zero. Or you can consider these three functions, sin x, 3 sin x and minus sin x on the closed interval minus 1, 2. They are linearly dependent. The first function plus the second function, that means 1 times this plus 1 times the second function plus 4 times the third function equals 0 for all x in this interval. So that's why they are linearly dependent. Here also all the constants, those ci's, are non-zero. But we need at least one of them to be non-zero. That's the condition. Next, we have the definition of linear independence, which naturally comes with dependence. It is actually just the absence of dependence. So again, finitely many functions are said to be linearly, this time, independent on a closed interval if they are not linearly dependent on that interval, which just means that these functions are independent on this interval if the following condition is true. Actually, this if is if and only if. I just wrote if. That if we find these constants such that the linear combination of these functions using those constants is equal to 0 for all x belonging to this interval, then all the constants have to be equal to 0. That is because if any one of them, at least one of them, is non-zero, then they become dependent. That's why. Oh, and one more thing, we don't always use the word linearly. Sometimes we just write independent or dependent, okay, as the case may be. For example, the functions x and x squared are linearly independent on the closed unit interval 0, 1. To see why, we take any two real numbers c1 and c2 and form the linear combination. And suppose we assume that this is equal to 0 for all x in 0, 1. Now, if we can show that c1 and c2 both have to be equal to 0, then that means these two functions are linearly independent on this unit interval. The fact that we have assumed that this is equal to 0 for all x in this interval means that we can put some specific value of x from this interval here, and then this should be true. In particular, we can take x equal to 1 because that's available to us. So we put that here and get this. This is equal to 0, or c1 plus c2 equal to 0, which means that c2 is equal to minus c1. So we use that value here and then get this equation. c1x minus c1x squared equal to 0, and still this is true for all x belonging to 0, 1. That's because this relation between c1 and c2, although we have used a specific value of x to find this relation, but the relation, the fact that c2 is minus c1 is independent of x because this does not have any x. So that is why for all x, c2 is minus c1. In fact, this being equal to minus of this has nothing to do with x. And then in this equation, we further put x equal to 1 divided by 2, which we can because that value is available to us, and that gives us this, which if you manipulate the left hand side, the equation becomes this: 1 over 4 times c1 is equal to 0, from which you get that c1 is 0. But because c2 is minus c1, so c2 is also 0. So that's how we are getting that c1 and c2 are both 0. So the initial claim that x and x squared are independent is true. And based on this notion of linear dependence and independence of functions, next we have this theorem, which is a fundamental fact about solutions of such equations, linear homogeneous equations. The nth order linear homogeneous equation always possesses n solutions which are linearly independent. Over what interval? Over some interval over which we are considering the differential equation. And also, every solution of this equation is expressible in this form as a linear combination of those n solutions, for some constants, of course, coming from the set of real numbers. So this just tells us that the solution space of such an equation, which actually is a vector space of functions, is n-dimensional with a basis consisting of n functions. That's what this tells us. In the next video, we are going to see more about this fact.